Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the concept of acceleration in 2 dimensions. And of course, this is going to be a follow-up discussion from the previous one, whereby we had looked at the concept of acceleration in 2 dimensions. Now, this is going to be assisting us try to describe this specific aspect of instantaneous acceleration. And as we said from our previous discussion, this basically is an acceleration at a specific point in time. And it's going to be described as the limit of acceleration as the time interval approaches 0. Now, I'm going to use these 2 specific illustrations for A and B, trying to explain this specific concept of acceleration in 2 dimensions. And of course, the second one for B is a familiar case which we have done in terms of a problem set from our previous video on the concept of velocity in 2 dimensions. So in this particular case, this is going to be the graph of a car that is moving along a curvature or an oval path, which is a track race. And of course, this guy is moving from a point 1 to 2 given in this specific illustration, which is going to be a displacement of 300 meters. So this guy is moving at a constant speed of 30 meters per second, and it's going to take a time interval of 40 seconds to cover this specific track. Now, we have done an evaluation of this specific problem in order for us to find this specific concept of velocity. And we said, therefore, that we're going to find this specific aspect of velocity. Perhaps we can just have a small revisit for the average velocity of this specific travel. So in this case, I've mentioned that this guy is going to travel at a constant speed of 30 meters per second. But we said that we can find average velocity. So this is going to be average. Let's give it in terms of velocity average. So we can find average velocity as the total displacement all over the time interval taken, given as delta x, delta t given as that. So in this case, if we look at this specific displacement and use the specific displacement given in terms of this one, we're going to see that a displacement is basically going to be a total distance from 1 to 2 along the x-axis, which is going to be a displacement of 300 meters, and then we're going to have this one taking, of course, 40 seconds. So we're going to have that one given as that, and this is going to be giving us a value of 7.5 meters per second as our velocity average. And if we try to look at this one, we understand that this guy is basically going to be traveling at 30 meters per second. So the difference in velocity is due to the fact that the guy is not going to be traveling along a straight line, and therefore we are going to see it displaying such a kind of a motion. And in this case, we can as well describe the concept of acceleration of this particular type of course, a car that is traveling along that path. Considering this specific, of course, information which we have been given, we're going to see that this specific aspect of velocity initial is given in terms of this specific aspect of 30 meters per second. And this is going to be the velocity component along that specific j direction, which is basically along the y-axis. And the velocity final in this case is going to be a negative component along the j direction, which is going to be given as a negative 30 meters per second, given as that one. So if we consider this 2 specific velocity component, we can evaluate the concept of acceleration by considering these 2 specific component in the j direction by giving acceleration in terms of the difference in velocity, which is a velocity final minus velocity initial, and of course that one divided by the time interval given as that one. So this is going to be giving us a value of negative 30 minus 30 meters per second given as that one. And this is going to be divided by the time interval, which is 40 seconds. So in this case, if we try to consider this specific evaluation, this is going to be giving us this aspect of velocity, which we are going to have given in terms of negative 1.5 meters per second square. So this is going to be in the j direction. As we said, the velocity and of course acceleration can be given either in the same direction or opposite direction, as in the case of a simple pendulum. But in this case, we're going to see that this specific velocity component, or the average acceleration during this time, the cast goes from point 1 to 2 is directed in the negative, of course, y direction, as we can see from this specific evaluation. So therefore, we're going to consider the aspect of acceleration in a 2-dimension just from this specific example which we have given, and see how we can generally illustrate this aspect of acceleration from this specific evaluation. So we're going to achieve that one using our first illustration, which I've just given on the board. And of course, we can consider this one to be the graph of velocity against the time. And therefore, the change in velocity against time of this specific graph is going to be giving us the element of acceleration. So in this case, I've just given these two specific points. And this, if we consider this specific point, perhaps A and B, we're going to see that the velocity component at this specific point is V1 and T1 for the time, and V2 and the T2 for the specific point of T. So in order for us to evaluate this one, we're going to consider instantaneous velocity as we acceleration, as we said, as the limit of the average velocity as the time intervals goes to 0. And this can be represented in terms of velocity is equivalent to the limit as the time interval delta t tends to 0 of this specific average velocity, given in terms of delta v over delta t, given as that. And of course, we're going to have this one represented from a representation of vectors. I said that this can be represented as a component of acceleration in the x direction, given as that one, plus the component of the y direction, given as that one. This is going to give us a general representation for this specific aspect of acceleration. Hence, we can find this specific ax, which is acceleration in terms of that one, given as a derivative of the velocity along the x component with respect to time. And similarly, we can have the velocity component along the x direction, given in terms of the derivative of vy with respect. So this is going to be along the y dt, given as that one. Now, from our previous discussion, we had mentioned the concept of circular motion, and we're going to consider this specific aspect of circular motion for us in trying to as well describe this specific aspect of velocity in terms of the x and the y component. And therefore, we have decided that we're going to have two specific descriptions for velocities in the x and the y axis, considering, of course, circular motion, whereby we said that the velocity component along the x-axis is going to be considered as basically a value of the negative omega r, the sine of omega t. And just shown, of course, from that specific discussion, that this concept of omega is angular velocity, and this is the radius, and this is going to be the time interval. Now, we have decided that basically these two specific aspects of velocity and, of course, angular velocity and omega are going to be constant values. And therefore, we said as well for the y component, we can represent this one in terms of r omega, the cosine of omega t, given as that. So if we look at these specific two components, then therefore we can describe acceleration in 2 dimensions by finding the first derivative of those two components shown on the board, whereby we're going to have acceleration along the x-axis is given as dvx over dt, which is going to be basically implying the derivative of this specific component, whereby we're going to have d over dt of the value of negative omega r, the sine over omega t. And of course, that's going to be giving us the concept of acceleration. So this is going to be giving us the value of this specific aspect of a negative, the square of omega, and then we're going to have r, the sine of omega t. So from evaluation of trigonometric functions, kindly confirm that this is true, whereby we're going to have the, of course, the derivative of the sine function given in terms of the derivative of the sine function given in terms of course, this is going to be just a minute. So this with respect to x, so it's going to be forming our, of course, a cosine function. So this is going to be cosine. The derivative of the sine function is going to be given as a cosine function, whereby we're going to have a negative omega r, the cosine of omega t. And then for us to find the, of course, the acceleration along the y component, this is going to be the d over dt of this particular function for the y, which is omega r, the cosine over omega t. Now the derivative of the cosine function is going to be negative sign, and therefore this is going to be giving us the acceleration along the y component in terms of a negative. So we're going to have a negative omega squared r at the sine of omega t. So, and those are going to form a specific representation for the acceleration component along the x and acceleration component along the y for those two specific representation. So in this case, these are going to be giving us particularly the representation for acceleration in 2 dimensions for those two specific components. But if we consider this a specific aspect for the perhaps the change in time against the change in velocity given as that one, we're going to have to use this aspect of Pythagoras theorem, as we said, by considering these two specific components in trying to evaluate that specific aspect of acceleration. So we have done this one from our previous example using the concept of velocity. And in this case, I'm going to employ the same strategy in trying to find this specific aspect of acceleration. So therefore, we're going to have the square of acceleration given in terms of acceleration along the x, the square of that one. And then we're going to have acceleration along the y, the square of that one. So in this case, we're going to have I and j, which are going to be a vector components along those specific direction. So we're going to do a substitution for those two specific aspects of course, omega and r, which we have had, whereby we're going to have a square of the first one given in terms of omega squared. So this is going to be a positive value. So the square of omega squared is equivalent to omega to power 4 r squared and the cosine of square of omega t for the first one, which is ax, and then we're going to have a sum of that one with the space is going to be enough. So we're going to have a sum of that one with omega. So the second one is omega to power 4 r squared, the sine. So that's going to be for the y, the sine of squared of omega t. So we're going to have this one factored out for omega to power 4 r squared, and then we shall have the cosine squared omega t plus the sine squared omega t. So in this case, this second section, as we said, is going to be giving us an identity which is going to be unity, implying that the square of acceleration is equivalent to omega 4 r squared, implying that acceleration is equivalent to the square of omega r given as that one. And that is going to be giving us the value of this specific constant value, which is going to be acceleration given in terms of those two representation for the 2-dimension motion given as such. So kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell to be getting updates on our various uploads in math and sciences. So that is it for now, guys. Bye. God bless you. Catch us in our next video.